Welcome to part 1 of this series on acoustics. In this video, we will be exploring the nature and properties of sound waves and introducing the concept of decibel scales for measuring loudness. Later in the series, we will be diving into sound transmission and insulation, room acoustics and vibrations, but for now let us begin with defining a sound wave. Mechanical waves fall into one of two main types. There are transverse waves or longitudinal waves. In simple terms, transverse waves have motion perpendicular to the direction the wave is traveling, such as electromagnetic waves or the vibrations of a guitar string. Longitudinal waves move particles parallel to the wave's direction of travel. Sound waves are longitudinal and will be the focus of the remainder of this video. The following equation can be used to describe how waves cause pressure fluctuations over time at a fixed point in space. One cycle of the wave measured between peaks is called one period. We can calculate the frequency in hertz from the period using the formula 1 divided by t. The angular frequency is the frequency in radians and can be calculated using the formula 2 pi f. To visualize this, imagine a speaker emitting sound and a microphone at a fixed position from the speaker. The microphone captures the pressure changes at that fixed position over time. However, to accurately describe how waves propagate through space, we need another equation. This equation is used to describe a snapshot of a wave in space at a fixed instant. We can think of it like pausing time to observe pressure waves along a line. Notice how the x-axis is now measuring the wave's position in space. One cycle of the wave in this domain is now known as the wavelength. From the formula, k is known as the wave number. It can be found by dividing 2 pi by the wavelength. While there is a relationship between frequency and wavelength, this formula only explains how waves behave in space and does not contain any direct time-related information. This final formula combines both functions to allow us to describe a wave in motion through space and time. Both the period and the wavelength can be observed in a single function. The relationship between the angular frequency and wave number can be used to find the wave's velocity. This function gives us all the information we need to describe the wave in time and space. The following example shows how peak pressure, frequency, and wavelength can be found from the combined wave equation formula. And this example shows how we can write a wave equation if we know the peak pressure and frequency of a wave. Each particle has a displacement, velocity, and acceleration associated with their movement. They all describe the same sound wave. When displacement is maximum, velocity is 0 and acceleration is highest. Think of it like a swing at its highest point. It pauses slightly before swing back. When displacement is 0, velocity is max and acceleration is 0. Like a swing rushing through the middle, it's at its fastest but not being pushed. The velocity wave is a cosine wave 90 degrees ahead of displacement. Acceleration is in phase with displacement but inverted. The following equations show the relationships between velocity, acceleration, and displacement. If we want to figure out velocity and know displacement amplitude, we use formula 1. If we want to figure out acceleration amplitude, we can use formula 2 or 3, depending on if we know the velocity or displacement amplitude. Pressure waves moving towards each other compress the air between, creating high pressure regions. Particles moving away from each other create areas of space and low pressure. This is known as compression and rarefaction. Pressure is related to the spatial rate of change of velocity, so pressure and velocity are also out of phase. For simple harmonic plane waves, under linear low amplitude conditions, pressure will be in phase with acceleration. This is because pressure is strongest when motion is changing most rapidly, in other words, at maximum acceleration. Pressure can be calculated by dividing the force in newtons by the area in meters squared. It is measured in Newton meters squared, or pascals. RMS pressure, or root mean square pressure, is a way of averaging pressure of sound waves. A simple average of pressure over time would cancel to 0 due to the constant positive and negative swings of the sound wave. If we know the peak pressure of a pure sine wave, we can use the following formula to calculate RMS pressure. Impedance is the ratio of the pressure to the particle velocity as shown in the formula. Similar to Ohm's law, it can be thought of that the acoustic impedance is the resistance to particle motion in a given medium based on the pressure-velocity relationship. It can also be shown that the impedance is the product of the density of a medium and the speed of sound in that medium. Sound intensity, or loudness of a sound wave, is the amount of energy passing through a given area in a given time. Intensity can be expressed as power in watts over the area in meters squared. Intensity is also equal to the product of the pressure and particle velocity. We can derive the particle velocity from the impedance relationship we explored earlier, as demonstrated here. This relationship tells us that sound intensity is proportional to the square of the sound pressure. Sound power is the measure of sound a source emits in watts. It is a property of the noise emitting object itself, unlike pressure or intensity, which are location dependent. Sound power can be calculated from the formula shown here. When talking about the loudness of a sound, we are actually referring to the intensity or pressure of a sound wave. The problem is that the human ear can detect a ridiculously vast range of intensities, from the quietest whisper to the roar of a jet engine. This would be impossible to plot on a normal scale. So, we use logarithms, specifically base 10, to compress the giant range of values into something more manageable, the decibel scale. To complicate things further, 3 decibel scales are used in acoustics. These are sound intensity level, sound pressure level, and sound power level. We will now take a look at each of these decibel scales and see how they are calculated. The sound intensity level is the decibel level of a sound relative to the sound intensity in watts per meter square. The sound intensity level is defined by the following equation, where I equals the sound intensity being considered, and the bottom number represents intensity at the threshold of audibility, 10 to the minus 12 watts per meter squared. If we use the equation to consider a sound with an intensity equal to the threshold of audibility, we can see that the intensity level equals 0 decibels. Alternatively, if we consider a sound with an intensity 10 to the 2 watts per meter square, we can see that the sound intensity level is 140 decibels, which is considered the threshold of pain. The sound pressure level is the decibel level of a sound relative to the sound pressure in Newton meters squared. Since the sound intensity is proportional to the square of the sound pressure, the sound pressure level is defined by the following equation, where P equals the pressure of sound being considered in Newton meters squared, divided by the reference sound pressure, 2 times 10 to the minus 5 Newton meters squared, or 20 micropascals. This is the sound pressure at the threshold of audibility. The following shows an example of a sound pressure level calculation using the pressure level formula. The sound power level is the decibel level of a sound relative to the source sound power in watts. It is given by the following equation. The reference sound power equals 10 to the minus 12 watts. And here is an example of how to apply that formula. Since decibel values are based on logarithmic scales, decibel values are not directly additive. This means that 2 sounds, each with a sound pressure level of 70 decibels, would not give a combined level of 140 decibels. A convenient method of adding decibel values together is as follows. This can be demonstrated in the following example. Decibel values can be subtracted in a similar manner as demonstrated in this next example. Thank you for tuning in to this video. In the next video, we will explore how sound intensity varies over distance and the calculations that can be applied to solve problems related to sound decay, which will lead us into exploring frequency analysis and sound transmission and insulation. If you found this video useful, don't forget to like and subscribe for more.